Hi everybody. In this tutorial, we'll learn how to use the T-formulae to model trigonometric graphs. So T-formulae are a type of equation that can be used to represent the sine, cosine and tangent functions. They're a really powerful tool for understanding and modeling trigonometric behavior. So in example 1, we've been told that the figure shows a graph of a function s, which is equal to 6 minus sine x minus 10 cos x, where x is greater than or equal to 0. And using t equals tan of x over 2, shown that ds by dx can be written as this function in terms of t. So the first thing we're going to do is we're going to differentiate this function with respect to x. So when we differentiate this 6, it goes, because it's a constant, this negative sine x becomes negative cos x, and the negative 10 cos x becomes 10 sine x. And just to make it easier, I'm going to write this positive term first. So now we've got this gradient function, we can use t equals tan of x over 2 to write sine x in terms of t. So 2t over 1 plus t squared. We can also write cos x in terms of t, 1 minus t squared over 1 plus t squared. And now we can substitute these values of sine and cos into our gradient function. So ds by dx will be 10 lots of sine x minus cos x. Now we can tidy this up by factoring out this common denominator. So now we get ds by dx. We have a 1 over 1 plus t squared outside the brackets, with 10 times the 2t to make the 20t, and then we've got the 1 minus t squared here. This is a positive when you multiply this negative by this negative. We can tidy up what's in this bracket, so this t squared term is first. So now you get the ds by dx and then t squared plus 20t minus 1. So we've shown that this is the gradient function for any point on this curve. In part B, we're going to find the coordinates of the first 3 stationary points. So that'll be the coordinate here, here, and here. Okay? So we know at these stationary points, the gradient will be equal to 0. So if ds by dx equals 0, then this equation will equal 0. And we can cancel out 1 over 1 plus t squared by moving it to the left-hand side. So this becomes 0. So now we get t squared plus 20t minus 1 is 0. And we can solve this equation using a quadratic formula. So t equals negative 10 plus or minus the square root of 101. And now we need to remember that this t is tan of x over 2. So our solutions then are tan of a half x is the negative solution, negative 10 minus root 101. And if we were to take the arc tan of both sides, then x over 2 will be negative 1.52 radians. But if we're looking at the first 3 solutions, here, here, and here, we need to consider other solutions to this. So we can draw our cast diagram. We have negative 1.52 here, but this will be equal to the solution in the second quadrant. And to work out this angle, we can have pi take away the 1.52. So the other solution will be 1.62. It's worth noting as well that this cannot be a solution because we're told that x has to be greater than or equal to 0. So this will be the solution from this equation. Other solutions will be when tan of x over 2 is the positive case. So negative 10 plus root 101. Again, if we were to take the arc tan of both sides, x over 2 will be 0.05, which we can show on our cast diagram. And the other solution will be in the third quadrant. So this will be pi plus 0.05. So the other angle, or the other value of x will be 3.19. So now we have our solutions for x over 2. We can work out x by multiplying each of these by 2. So our x values are 0.1, 3.24 and 6.38. We can substitute each of these into our equation for s to work out the corresponding s value. So our first coordinate will be here, 0.1, negative 4.05, here, 3.24 and 16.05, and then finally at this point, 6.38 and negative 4.05. Okay? So in example 2, we're going to look at a similar equation, but this time involving double angle formulae. Okay, so in example 2, we're told that the figure shows a graph of a function h, which is 5 plus 4 sine x minus 2 cos 2x. Again, where x is greater than or equal to 0. And again, we've been told using t equals the tan of x over 2, shown that this is now the gradient function. So do you want to try this question yourself, using the T-Formulae? You can pause the video, and when you come back, we'll go through the work solution. Okay, so welcome back if you had a go. So the first thing we're going to do is we're going to differentiate h with respect to x. When we do this constant 5 will go, the 4 sine x will become 4 cos x, and using the chain rule, negative 2 cos 2x becomes positive 4 sine 2x. And again, if t is equal to tan of x over 2, we can write sine x as 2t over 1 plus t squared, and cos x as 1 minus t squared over 1 plus t squared. And now we can substitute each of these into here. So now we get 4 lots of cos x. The sine 2x we can write using the double angle formula, and then we can substitute this in place of sine x, and this in place of cos x. We can multiply the 2 by the 4 to get the 8, and then we have sine x cos x. Now at this point, you can notice in our question we have the denominator of 1 plus t squared, all squared. Well, we get that from these two terms, but we need to multiply this fraction by another 1 plus t squared. So if we multiply it by the numerator and denominator, these two will effectively cancel, so we get back to here. But now we can factor out the 1 plus t squared all squared. We also have a common 4 here and here. And we have a common 1 minus t squared on the left hand side and on the right fraction. So we can factor out the 4, the 1 minus t squared, and the 1 plus t squared all squared. And what we're left with is this term, 1 plus t squared, and 4t. So we've shown that this is the gradient function in terms of t for this graph here. And now we need to use this gradient function to find the values of x for the first 4 turning points. So here, 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 and here. So to find the x values of the first 4 turning points, we know at each turning point the gradient will be 0, so we can make this equation equal 0. We can move the 4 over 1 plus t squared all squared to the left hand side, so 1 minus t squared will have to equal 0. And if this is 0, we know that t must be plus or minus 1. Our other solutions will come from this quadratic. T squared plus 4t plus 1 is 0. And we can solve this, so we get t is minus 2 plus or minus root 3. So we've got 4 solutions, 1, 2, 3, and 4. So remember that t is tan of x over 2. We can begin by looking at this solution, the negative 1. We'll take the arctan of both sides. So x over 2 will be negative pi over 4. We can multiply it by 2 because we want x, not x over 2. So x will be negative pi over 2. And within the range of x being greater than or equal to 0, we know that x will be 3 pi over 2. This will be the positive solution. If we now look at tan of x being the positive one case, again take the arctan. We know that x over 2 will be pi over 4. Solving this for x, we get x will be pi over 2. Our next solution will be tan of x is negative 2 plus root 3. So in this solution here, take the arctan, so x over 2 is negative pi over 12. And multiply this by 2 to find x. So x is negative pi over 6 and negative 5 pi over 6. Neither of these solutions fall within the correct range where x is greater than or equal to 0. So finally, if we now look at tan of x over 2 being negative 2 minus root 3, x over 2 will be negative 5 pi over 12. We can multiply this by 2, so x will be negative 5 pi over 6. And within our range, this will give us 7 pi over 6 and 11 pi over 6. So here, we'll have pi over 2, 7 pi over 6, 3 pi over 2, and 11 pi over 6. Okay? Well, thank you very much for watching, and I hope you found that useful. If you did find that helpful, please like and subscribe. And you can download the full lesson and worksheet from my website, mrmathematics.com. There's a link in the description below. Thanks again, and take care.